So let's talk about how we can trade off bias and variance. How do we regulate bias and variance? Well, one way is to get more data. Getting more data addresses variance. The more data you have, the less you will overfit and the less variance you will suffer from. So if we have very little data, if we have maybe 5 data points and we're fitting an 8th degree polynomial, we're likely to overfit. If we have 5 million data points and we're fitting an 8th degree polynomial, then we'll probably be fine. Right? So if we had a huge amount of data like this, then probably that complicated function class would actually fit the true function pretty well. Getting more data doesn't generally improve bias. So that's the underfitting example from before. That straight line is not going to fit the true curve no matter how many data points we give it. You can change your model class. Changing your model class basically means change your program. Maybe you have more values in theta. You have a larger parameter vector. You have a more complex program. For example, you can take your 12th degree polynomial and change it to be a linear function. That'll probably reduce variance and increase bias. Right? But that's a very discrete choice. Can we somehow more smoothly restrict the model class? Like, maybe we really want 12th degree polynomials, we just don't want them to be quite so crazy. We don't want them to be quite so peaky and jagged and sharp. Can we somehow construct a kind of a continuous knob for complexity? So this is called regularization. Regularization, informally, is something we add to the loss function, typically to reduce variance, although not always. Perhaps one of the easier ways to understand regularization is through the Bayesian interpretation, which regards regularization as a prior belief about our parameters. I'll explain this in more detail shortly. But keep in mind, this is not the only interpretation. There are other ways to understand regularization too. So the high-level intuition for the Bayesian perspective is this. When we have high variance, it's because the data doesn't give us enough information to identify the parameters. So if we only have those 5 data points and we have a 12th degree polynomial, the problem is that the function is just underdetermined. There are many different 12th degree polynomials that all fit those 5 data points really, really well. So among all those 12th degree polynomials, we don't know which one to pick. Right? They all look equally good. And maybe some of them are a little bit better than others. There's also noise in the data, so we might not even want the one that's the best fit. But deep down, the issue really is that there's not enough information in the data to pick one of the many possible functions, which all look equally good in terms of the empirical risk. So we need to somehow provide a little bit more knowledge. So if there's not enough information in the data, can we give more information to the algorithm through the loss function? And if we provide enough information to disambiguate between a bunch of almost equally good models, maybe we can get the algorithm to actually pick the right one. So if we have our data set here, these are all identical data sets. I'm just going to show different functions. We have a bunch of different functions that we could draw that all look equally good in terms of their empirical risk. So the first one, the second one, and the third one, they all go straight through the blue points. But even if you didn't know what the data set was, and I just showed you those curves, maybe you might have a preference for which of them kind of looks better, which of them is more likely to be right. Like that second one, probably not the right answer, right? It could be, it's not out of the question, but probably not. Like, probably the functions you care about just don't look like that. So all these solutions have zero training error, but what makes the third one better? Of course, this is situational. It might not be better. It may be that you know for a fact your function is like super jagged like this. But just from sort of your knowledge about the domain, your knowledge about the problem, you might guess that the third function is a better one, even if you didn't know what the true function looked like. So the Bayesian perspective can be formalized like this. You can ask the question, given a data set D, what is the most likely parameter vector theta? That is, in a sense, the learning problem. But we can write out the entire learning problem probabilistically. So before, in the previous lecture, we wrote out the prediction problem, how to get y from x, probabilistically. Now we're going to write the entire learning problem probabilistically, the problem of how to get theta from D. So D, remember, is just a set of xy tuples. And if you want the distribution over theta given d, you can just apply the definition of conditional probability. P of theta given d is equal to P of theta comma d divided by P of d, which up to a constant of proportionality is just the joint. So we can always renormalize, so let's just ignore the denominator for now and just say that it's proportional to P of theta comma d. And by the chain rule of probability, we can factorize this as P of d given theta times P of theta. Okay. Now, we've actually seen this first part before. The probability of d given some parameter vector, using the IID assumption that we discussed in the previous lecture, can just be factorized as a product over all of your data points of P of xi times P theta of yi given xi. We don't control P of xi, so it's really the P of theta yi given xi that matters to us. So that's just our maximum likelihood objective that we saw in the previous lecture. And remember that P subscript theta of y given x is just a notational shorthand that I'm using for P of yi given xi comma theta, right? We're really conditioning on theta. So what's that second part, right? There's a new thing that showed up once we wrote this out using the definition of conditional probability, and that's the P theta. What is that? Well, P of theta is how likely theta is a priori, how likely you think theta is before you've even seen the training set. And this is called our prior, because it is our belief over theta a priori before you've seen the data. So without knowing the true function, without even knowing what the blue circles are, look at these two graphs, the spiky one and the smooth one. If I ask you, well, which of these do you think is more likely to be a true function? If you believe that smoother functions are more likely, you might say the second one. If you believe that spiky functions are more likely, you might say the first one. So that's essentially the role the prior plays. But of course, what I've told you so far is maybe not all that useful because I haven't told you actually how to build a prior. Like P of theta is some function, could be anything, right? How do we actually build P of theta priors that select the smooth function, the second one, as opposed to the spiky one, the first one? So we'll get to that in a second, but let's just finish this line of thought. Using this kind of Bayesian formulation, we have a new loss function. So before we had negative log likelihood, now we have a slightly different negative log likelihood. We have our first term, so we're just going to take the log of that P of d given theta times P of theta. When we take the log of a product, we get a sum of logs. The log P of d given theta is just the log likelihood from before, and it's a loss, so it's negative log likelihood. So that's just the sum over all of your data points of log P of yi given xi comma theta. It's exactly the same as what we had before in lecture 2. But now we also have this log P of theta term tacked on at the end. And that's our prior. So all you do is you just subtract your prior from your loss. Very simple. And we have to choose it. We have to choose what that log P of theta is, and that is a design choice that we make. It doesn't come from the data, it is our prior belief. Okay, so can we pick a prior that makes smoother functions seem more likely? A prior that makes that second curve, the smooth curve, appear more likely than the messy curve on the left. Well, what kind of distribution assigns higher probabilities to small numbers? That's what we're going to want. Why small numbers? Well, consider the example in the bottom left of this slide. The example here is linear regression with polynomial features. That's actually what I've been showing you when I showed these messy overfitting curves. So linear regression with polynomial features just means that your f theta of x is theta 0 plus theta 1 times x plus theta 2 times x squared plus theta 3 times x cubed, etc., etc., etc. This is a linear regression model, right? Because the function is linear in theta. It's not linear in x. That's just because we're introducing features. The features are 1, x, x squared, x cubed, etc. Polynomials that look like the ones in the lower left generally tend to have large coefficients. They need those large coefficients to be able to make these big spikes and big jumps. If we only allow polynomials with very small coefficients, we'll get curves more like the one in the bottom right. Right? With small coefficients, you can't have these big spikes. So if we want small coefficients, we can ask, well, what kind of distributions assigns higher probabilities to small numbers? There's actually a wide range of distributions we can choose from, but one very, very simple choice is to use, again, a normal distribution, this time with a mean of 0. So a normal distribution with a mean of 0 looks like a bell curve. It puts most of the probability mass on small numbers close to 0. How close? Well, that's determined by the variance. So sigma squared is the variance, and that determines how close you want to stay to 0. Okay, so that's a simple choice for a prior. We can select p of theta to be just a normal distribution with a mean of 0 and a variance of our choice. The lower we choose the variance to be, the harsher this prior will penalize functions with big spikes. Okay, so let's talk about this thing a little more. Again, here is the expression for the log probability of a normal distribution with a mean of 0. So we sum over all the dimensions of theta, and for each dimension, we have negative 1/2 times theta I squared divided by sigma squared minus log sigma minus 1/2 log 2 pi. Right. Now, the only thing here that depends on theta is actually the first term. The second and third term, they don't influence theta, so we can disregard them, because no matter what they are, they won't affect the optimization over theta. So we can equivalently write this normal prior as negative lambda times the norm of theta squared plus some constant, where lambda is just 1 over 2 sigma squared. Crucially, we don't care that lambda is equal to 1 over 2 sigma squared, because we're not actually going to be picking sigma, we'll just pick lambda directly. So we don't actually care about this, we'll just select lambda directly, but it helps to know how it connects to a normal distribution. Okay, so after all of this motivation, all this math, all we ended up with is a very simple prior term, negative lambda norm theta squared. And when we subtract that from our negative log likelihood, we just end up with our mean squared error, that's what negative log p of y given x is, plus lambda theta squared. Why plus? Well, because we're minimizing this. And lambda here is what we call a hyperparameter. Lambda is a design decision that we make ourselves. Lambda is not a learned quantity. Lambda is chosen so as to impose the correct prior, the prior that we believe will give us the correct answer. So after all of this motivation, all this complexity, all we ended up with is the same objective we had before, the sum of these squared errors, and all we've done is we added lambda norm theta squared to it. That's it. But we know now that this corresponds to a Bayesian approach where we have a prior distribution on theta, and that prior is normal with mean 0, and a variance that can be deduced from the formula in the bottom left of the screen. But you don't actually have to do that. You don't have to deduce what sigma is. You can just pick lambda directly. And of course, this is the case if the variance for our prediction is identity. Okay, so this term is the only new thing we've added. All right, so that's regularization for linear regression, for regression problems. What about classification? Let's talk about logistic regression, which we discussed from the previous lecture. So in the previous lecture, I showed this very appealing picture of logistic regression with the softmax learning this lovely distribution where you have a probability that's 50-50 in between two classes, and then the probability smoothly increases towards red on the red side and smoothly increases towards blue on the blue side. But that's what we wanted. What if what we got was more like this? Like the green stuff assigns 100% probability to red, the blue stuff assigns 100% probability to blue. Training accuracy is perfect. But the shape of that decision boundary in between the red and blue is junk. Like, that is not the correct decision boundary. In fact, this probably has high variance. If I were to move those points around, the decision boundary might change drastically. So it's just like the overfitting we had before, only now for logistic regression. So technically every point is classified correctly, but this is grossly overfitting. Okay. So one way that we could devise a regularizer for logistic regression is to think back to the example that I gave in the previous lecture when I had this 1D example and I was explaining why we call the softmax a softmax. I talked about how if you just take theta and you multiply it by a big number, you get a much sharper decision boundary. You basically get much sharper probabilities. Perhaps if you multiply theta by a really big number, the probabilities will just jump straight away from 100% blue to 100% red. If the theta values are small, then the probabilities are smoother. So large theta values means sharp probabilities. Small theta values means smooth probabilities. So perhaps if you want smooth probabilities, if you want something like the nice picture on the left, maybe what you want is just smaller values of theta. So, simple idea. Why don't we put a prior on theta that favors small numbers? What kind of prior can we use? Well, we can use a normal distribution with a mean of 0 and some variance sigma squared, which reflects how much we want those smaller values. So the actual loss will be exactly the same as before. We'll just take our log probabilities. I apologize, there's a missing negative sign, so this should be negative log probabilities, and we'll add lambda theta squared to them. So it's the same prior, actually. It's the same zero mean normal prior, but now for a classification problem. And this is sometimes called weight decay, because in this minimization problem, we are minimizing the weights, so we're kind of decaying the weights. We're making them smaller. There are many other examples of regularizers, and we'll discuss some of them later. So I presented two examples that both happen to be a normal distribution with a mean 0. That is the most common kind of regularizer, particularly in deep learning, referred to as weight decay, but it is not the only choice. One common alternative choice is to use the absolute value of theta instead of the square of theta. At first, this might seem like a very similar choice. It also favors small numbers, but it has a very different shape, right? So the absolute value function has constant slope, whereas the square function has increasing slope. One of the things that this absolute value regularizer does is it encourages as many entries as possible in the vector theta to be 0. It encourages what are called sparse solutions, ones where not all theta dimensions are used. The reason for this is a little bit tricky to understand at first, but there's a geometric analogy that can help. So here I have two pictures, and let me explain what these pictures mean. So those ellipses, the kind of reddish-purple ellipses, those denote contours of a log likelihood. So that's basically the first term in the loss. And these concentric circles indicate circles of increasing log likelihood. So if you didn't have any regularizer, you would just go straight to the middle of the innermost ellipse. The bluish shapes, the diamond and the circle, those represent contours of our regularizer. So each color is kind of a different value for the regularizer. Now, the regularizers all try to drive the weights towards 0, so the lowest value of the regularizer is attained when the weights are 0. But of course, these two terms have to trade off against one another. So intuitively, what you're going to find is a point in parameter space where the regularizer and the likelihood balance out. So it'll be kind of an intersection between contours of the likelihood and contours of the regularizer. For the normal regularizer, for the weight decay, the one on the right, the contours are circles, right? Because squared norms trace circles in the space, right? So that means that the point that you will actually find will be one where the ellipse touches as tangent to one of those circles, because that's where they're going to trade off against one another. And that's kind of what you see, is that the little dots there represent the solutions you'll find for different weights on the regularizer. And as you might expect, you just kind of move outward from the innermost ellipse as you increase the weight on the regularizer. For the diamond shape, the parameters are allowed to move closer to the loss ellipse when you zero out one of the values. So what you see there is that essentially the least useful parameter is decreased first until it gets to 0, and then the other parameter gets decreased further. So these diamond-shaped contours actually result in a regularizer that promotes sparsity, promotes zeroing out any theta values that are not too useful before driving down the others. So it creates a preference for zeroing out dimensions. Colloquially, this absolute value regularizer is sometimes called L1 regularization, and it corresponds to something called the Laplace distribution. The weight decay, the squared regularizer, is sometimes called L2 regularization. That comes from the notion of L2 norm versus L1 norm. Another regularizer that's used sometimes with deep neural nets is something called dropout. It's a special kind of regularizer for neural networks. We'll discuss that a lot more later. Some types of neural networks, like generative adversarial networks, the kind that generate pictures of faces and animals, they have their own special regularizers that people use, like gradient penalty, and we'll discuss those a lot more when we talk about GANs. And there are, of course, lots of other choices. So you will see many algorithms and many different models that just use weight decay. That is probably the most common type of regularizer, especially in deep learning. You will see quite a few methods that use L1 regularization in one way or another. You'll see some methods that use dropout and some methods that use more specialized regularizers for particular types of models, like gradient penalty. Okay, now I presented regularization from a Bayesian perspective, where the regularizer encodes prior knowledge about parameters. But that's not the only way to look at a regularizer. There are other perspectives on regularization that are also important, that also teach us something about the role that regularization plays. For example, you can take a numerical perspective on it. You can think of a regularizer as something that makes an underdetermined problem well-determined. So imagine that you're doing linear regression, and you have more features than you have data points. As an exercise in your own time, you could actually work through the normal equations for linear regression when there are more dimensions in X than there are data points. And what you will find is that the matrix that you invert in linear regression becomes singular, becomes non-invertible. That's a numerical problem. It turns out that the L2 regularization approach I described can also be regarded as addressing that numerical problem by taking a singular matrix and making it non-singular by adding to its diagonal. I'm not going to go through the derivation of that in class because it's just going to be throwing more math at you. But if you would like, you can go through on your own time and try to actually work out those equations or ask one of the TAs in section. You can also take an optimization perspective on regularization. So far, we talked about regularization as kind of a way to reduce overfitting, but you can also in some cases use regularization to make it easier to optimize the loss landscape. So perhaps paradoxically, a regularizer can sometimes reduce underfitting if the underfitting was due to poor optimization, and the regularizer was chosen very carefully to reduce those optimization challenges. And this is actually one of the ways in which deep learning can sometimes deviate from our conventional wisdom in shallow machine learning, because in deep learning, sometimes regularizers actually reduce underfitting rather than overfitting. This is especially common for models like GANs, generative adversarial networks, and we'll talk about that a lot more in a subsequent lecture. I just wanted to mention it now just so that you're aware that regularizers can play a variety of different roles. So in machine learning, any kind of heuristic term that we add to the loss that doesn't depend on the data is generally called a regularizer. And one thing about regularizers is that regardless of which perspective you take, and regardless of what role they play, they generally introduce hyperparameters that we have to select in order for the regularizer to work well. A hyperparameter could be as simple as that lambda, so it could be as simple as a multiplier in front of the regularizer, or it could be something more complex. But one way or another, these hyperparameters have to be chosen, and they can't be chosen to minimize your training loss, because your training loss might already be very, very low if you're overfitting, for instance. So you have to choose those hyperparameters in some other way. And that's what we'll talk about in the next section.